just this year, 20 years after the publication of this book, okay, a book with more detail and further developments and so on was published by Cambridge University Press. This is a book by Jean-François Martens, Sylvain Sorin, and Shmuel Zamir, published just a couple of months ago. Now, as I said, this is meant to be teaching, so please interrupt. If anything is not clear, interrupt, ask, discuss. As Professor Maskin said in the first lecture, this is a school, it's not a seminar. And therefore also I'm not going to use the what's it called, the PowerPoint. Yes, I'm not going to use that kind of presentation. I'm just going to write on the blackboard. It's for a number of reasons. First of all, I am very technologically challenged. I can't overcome the PowerPoint. It takes me a long time. That's the real reason. But there are some excuses also. And the excuses are that these PowerPoint presentations, the slide is on, the slide is off, you don't see it. As you, if you write on the blackboard, when I was in a city college, and that's about 70 years ago, okay? 65 to 70 years ago, I gave seminars there in the math department, and Professor B.P. Gill told me the board eraser lesson number 1. You start at the left side of the board, you write, you never erase anything until you get to the right side of the board, and then you start again on the left side, erasing only as is needed. So everything is going to be in front of you, and it's a good way of teaching math, and there's going to be some math today, although we'll try to keep it intuitive. Now, you'll see there on the left side of the of this display, you see the the cover of the game of the book by Marshler and me, Repeated Games with Incomplete Information, and it has a cloud reminiscent of a nuclear explosion, okay? And that's really what it's meant to be. And the history of this is as follows. The Arms Control and Disarmament Agency of the United States was in the business of trying to negotiate with Soviet Russia on reducing the amount of armament. So this was arms control. The emphasis was on arms control, and disarmament was not really on the books at that point. And they reached out to a firm called Mathematica in Princeton, New Jersey. This firm was run by the principals and the former Oscar Morgenstern, who you may have heard of. He is he's the mother of game theory, okay? I like to say that von Neumann is the father of game theory, and Morgenstern the mother. And thank you. So he's one of the two originators of game theory, and he and Harold Kuhn both are no longer with us. Morgenstern passed away in the late 70s, and Harold Kuhn passed away last summer, I think, right? So Harold Kuhn was a very prominent game theorist, but he was a young man at that time, so he passed away just recently. Now, the ACDA, the Arms Control and Disarmament Agency, turned to to Mathematica Incorporated because they realized that these people were game theorists, and maybe the game theorists could help in giving ideas for conducting these negotiations. And Mathematica assembled a team of economists and game theorists. It included Michael Maschler and myself. Later Dick Stearns. It included Herb Scarf, John Harsanyi, Reinhard Selten, Herb Scarf, Gerard Debreu, a whole bunch of fairly prominent people, shall we say, okay? Present company accepted. And we got to work on trying to say something to advise the ACDA. And one of the problems was, one of the situations there was that they had, every year they had a conference in Geneva. So they had Geneva conferences year in and year out to try to reduce the amount of atomic weapons that are being stockpiled. And these were repeated, so this was a repeated game. These negotiations constituted repeated games. They were every year, again and again. And they were repeated games of incomplete information. Why were they of incomplete information? Because the important element over there is not what the amount of nuclear weapons destroyed, but the important element is the number of nuclear weapons remaining after some are destroyed. And you could specify the number destroyed, and you could make inspections to see that, that this really was done, but you could not know how many were there in the first place, okay? So this was and that's the important parameter, the number remaining, not the number destroyed. So this was very much a repeated game of incomplete information. And various people of this team that I mentioned got to work on various aspects, and Mike Maschler and I decided to tackle this element of a repeated game with incomplete information. And we decided to go, I'm going to go in this lecture, I'm going to try to go through the research process. The research process took a long time, many, many months, and in fact it took us about a year to get to the original result that I'm going to present you with now. But I'll try to walk you through it and see what Mike and my thinking was on this issue. So we started with very, very, very simple situations. We started with, now this situation that I'm talking about over here is not a zero-sum game, okay? The Geneva Conference negotiations are not a zero-sum game, and it is repeated and incomplete information, but the incomplete information is on both sides. The Russians didn't know what the United States has, and the United States didn't know what the Russians have. So there was incomplete. But we decided to tackle first, just to start with, the very, very simplest situation. So we said, okay, let's talk about a zero-sum game, a zero-sum repeated game, and the business of incomplete information on both sides is complicated. Let's see first what happens when there's incomplete information on just one side. Okay, so we'll start. I don't know exactly. Even the technology of this blackboard is a little daunting for me. But okay, let's see what we can do. We'll start out on this. Well, on this. Okay. So we took a look at a two-person zero-sum game of incomplete information, and that is this one. Okay, so the payoffs are, as in any zero-sum game, that the player won. And this is one possible game that is being played, and the other possible game is this one, 0, 0, 0, 1. And nature chooses either this one or this game with probability a half each. And then the chosen game is repeated. Okay? The chosen game is repeated. So we get this again. 1, 0, 0, 0. You can hardly think of anything simpler than this. But it's still pretty interesting. Okay? And it's repeated again and again. All right? A lot of times. And now what happens is that player one is informed which of the two games nature chose. So P1 knows the true game. P2 does not. Okay? However, P2 is informed of the choice of P1 after each stage of the game. So the first stage, P1 chooses either up or down, okay? Up, down. And P2 is not told which game it is. He is told of P1's choice. Okay, he is not told of the payoff. The payoff, just like in the arms reduction, arms control case, the payoff comes afterwards. Yes, we hope it doesn't come at all. Yes, but it comes afterwards. Or at the, in fact, the payoff came afterwards, yes, and the payoff was, in this case, pretty good. But the payoff is not told to the players at each stage. So neither to player one, player two. Of course, player one knows, because he knows what player two did, he knows what he did, and he knows what the game is. He has complete information. So he knows, but P2 does not know. And now what we want to ask is, what is the value of this situation? Okay, what is the value of a long repetition? So now what does long mean? And we can have various definitions of long. One possibility is to look at the end stage game. So we call the game, this game we call this gamma, okay? And we have various ways of representing gamma. So we can take a look at an end stage game, gamma n, and we can take a look at its value. Okay, value of gamma n. Now what is the payoff in gamma n? The payoff in gamma n in the end stage game it's the average payoff. It's not, we don't look at the total payoff, we look at the average payoff, because the total payoff may go to infinity. It's not a very useful item. So gamma n would be, let me write so the payoff in gamma n would be 1 over n sigma j equals 1 to n h j or h, in fact, h of hj of sigma n tau n. Let me explain what that means. It's just, you know, maybe I shouldn't even put this heavy math on the board. We have a strategy in the end stage game. That is the strategy of player 1 in the end stage game, sigma n. We have the strategy of player 2 in the end stage game. We call that tau n. Okay? This yields, at each stage, it yields a payoff to player 1 and to player 2. Okay? Basically, it's a zero-sum game, so it's a payoff to player 1. So this is the sum of all the payoffs in the at the various stages of the end stage game. We take the average, so that's the payoff in gamma n. Okay, and there's another way of looking at it, and that is an infinite stage game in the first place. Okay. We look at a infinitely many stages, and that we call that gamma infinity, and the payoff in gamma infinity is, well, I'm going to put it in quotation marks, is the limit of 1 over n sigma from j equals 1 to infinity, sigma from 1 to n, h j, sigma infinity, tau infinity, okay? That is that, and we put that in quotation marks. Why are we putting it in quotation marks? Because the limit may not exist. You have to work with lim inf and with lim sup and stuff like that. I'm not going to worry about that over here. I want to get to the main point. So there's a way of defining this exactly. I'm not going to put it down. I'm just, maybe the quotation marks should come around the word limit. Okay. There's some way of defining this. The important thing is that we're talking here about infinite state, one strategy for the infinite stage game. We're not talking about different strategies for the end stage game, okay, for each n. We're talking about a single strategy for the infinite stage game. So that is gamma infinity. And now we can look at, there's also a way of defining gamma delta. This is the discounted game as the okay, I'm not even going to write the formula for this. There's a way of writing. It's very straightforward. I don't want to take the time for it. So we have a okay, and now what we say is that we look at that we're going to say the theorem, which I'm not going to prove because I want to get to more substance, is that lim as n approaches infinity of the value of gamma n is equal to the value of gamma infinity and is equal to the lim as delta approaches 1 of value of gamma delta. Okay? So all these things are the same. It's all the same, different approaches to defining a long game all lead to the same result. Okay? So we don't have to worry about which is the right definition. This is not always the case. this is the case in the particular situation that we are looking at, and that is zero sum and incomplete information on one side only. In that case, all these are the same. All right, let's now get back to our game. Okay, so if the game is played only once, all right, in other words, if we truncate over here right after the first stage, then player one has a big advantage. Right? He knows what the game is. He doesn't have to worry about giving hints about the next stage. He just plays, if this is the true game, he plays up. If this is the true game, he plays down. That's it. That's the end. What about player two? He doesn't know, right? So what can he do? The best he can do is randomize half-half. So the value of the one-shot game is value of gamma 1 is a half. All right. Okay. Now let's take a look at a two-stage game. In a two-stage game, you could say also, why doesn't player one simply play top here or up here, and if this is, and down on this side, and then he can get, and player two doesn't know. But that is not the right answer, because if that would be the optimal strategy in the two-stage game, okay, value of gamma 2, if that would be the optimal strategy in the two-stage game, then player 2, the uninformed player, would know that that's the optimal strategy, right? Because in a two-person zero-sum game, the optimal strategies are equilibria. And in equilibria, you can announce your equilibrium strategy, and the other player can't do anything about it. He said, "That's my equilibrium strategy. Now do me something." Okay, so if that was the optimal strategy for him to announce one in the first stage game to play up or down according to which game it is, then he would be able to tell player two, and then player two would know. So okay, on the first stage he doesn't know before the first stage, but after the first stage he'll be able to tell which game it is from what player one did at the first stage. So at the second stage, he just does the opposite. If this is a true game and player one played up over here, then player two will play right, yes? And so the outcome will be 0, okay? So he'll be giving the game away, player one. So he'll get half on the first stage, okay? But he'll get nothing on the second stage. So the average is a quarter. Can he not do better than a quarter? That is the question. And the answer is yes, he can do better than a quarter, because what he can do is to randomize on the first stage, okay? And he announces that on the first stage I will randomize, okay? And then he will get an if he plays half-half over here, okay, on the first stage, then player then the value of the randomized game is, so you'll play half-half, so he's not distinguishing. So what we have over here is basically he's playing half-half. So we have half of this matrix plus half of that matrix is half-half, 0, 0. Now player 2 responds to this optimally, and you get the value of this game on the first stage. The result then is, on the first stage, you get you get 1/4, okay? On the first stage, you get 1/4. Then on the second stage, okay, so he has revealed nothing at the first stage, all right? On the second stage, now this is the last stage, he doesn't have to worry about giving information away. So on the second stage, so this is first stage, stage 1. On stage 2, he can take full advantage of his information, and so, like we saw before, get a half. So the total payoff will be a half plus 1/4 equals 3/4. Average is 3/8. Okay. So he can get at least, by doing this, he can get an average of 3/8, which is better than if he would have given the game away right away at the first stage. So we have over here, player 1 can get 3/8. In fact, the value of the two-stage game over here is 3/8, but I don't want to now get into the business of proving that it is that's the best for him. I want to get straight to the infinite stage game. All right. Is there any player 1 does have an advantage, seems to have an advantage in the long stage, because he has information, and player 2 does not have information. So to what extent can he make use of this information? What can he gain in the infinite stage game? The answer is he can't do anything. He cannot get any information. He cannot get any advantage in the infinite stage game or in the long stage game. We're going to prove that value of, for this game, value of gamma infinity equals 1/4. Now 1/4 is, as we said before, it's exactly the value of the oh, there's a problem over here. I'm all wired up. Oh, wait. Okay, I got it. So the value is 1/4, i.e. no advantage to the informed player. So P1. Okay? Now, we saw that in the one-stage game, if P1 ignores his information, this is the one-stage game. The value of that is 1/4. So if you play if he ignores his information throughout the infinitely many stages, then you get a repeated game, a repeated zero-sum game of complete information has the value of the one-shot game. Okay, nothing happens, and the repetition doesn't change matters. So it's as if player 1 had no information, as far as he cannot extract anything from his information. So now let's prove this. Okay, we will prove this. see. Now we're going to cover this up. Yeah, this is too complicated for me. You know, the old blackboards where nothing rolled, yes, you could just start on the left and keep writing until you get to the right end, and then erase what you started on the left. But that's with modern technology has even come into blackboards. All right, we'll prove this theorem. All right, this theorem. Proof. Okay, so one, the value of gamma infinity is greater than or equal to a quarter. Well, that's obvious because, in fact, P1, the informed player, can ignore his information. That's an option that he has. If he ignores his information and never makes use of it, then he will be getting a quarter at every stage, so the average will also be a quarter. Okay, now we have to prove 2, and this is the harder part, that value of gamma infinity is less than or equal to a quarter. Why is that? Now, the reason for that is that if P1, if player 1 makes use of his information, then if his strategy makes use of his information, then, as we said before, he can announce the strategy to the other player. So the other player, in any case, he can announce the strategy to the other player. So if he makes use of his information, then the other player knows that he will sometimes be playing differently, whether the true game is the left game or the true game is the right game. Whether it's this, whether nature chose this or that. He will be playing differently. So from the way he plays, the uninformed player will be able to deduce something about the true game, okay? And that, in the end, is going to be the undoing of the informed player, because he'll be giving he will be implicitly giving information away. That is the idea of the proof, and what it is based on is what I call the probability convergence theorem, and this is the main idea of this lecture, one might say. The probability convergence theorem is like this. Let omega be a state of the world. So if you want to say this in probability terms, it's a member of the probability space. But in less formal terms, we call it a state of the world. And E, an event. E, an event. P1, P2, and so on. An infinite sequence of the probabilities, and these are the probabilities of the event E, given more and more information. Okay? More and more information about what? About the state of the world. Then this sequence Pn almost surely converges. I tried to write this in fairly non-mathematical language. Let me translate it into mathematics. Okay? We have a probability space. We have points in the probability space. And now we have more and more information, which means information is given by sigma fields, which become finer and finer. Okay? You get finer and finer sigma fields, then the probability of the event E at the state of the world omega. So in other words, it's conditional on the element of the sigma field in which omega is given. Now that will converge almost surely. But I think it's better to think of it in this more intuitive statement. And this, in fact, I call it the probability convergence theorem. It's in fact what's called the Martingale convergence theorem. Okay? Probabilities are a martingale. Those who don't know what a martingale is, forget what I'm saying. Probabilities are a martingale, and there's a bounded Martingale convergence theorem. This is a special case of it. Okay? But this is true. This is a mathematical fact, not terribly easy to prove, but not terribly hard either. Okay? It's not something that I want to get into in this lecture. All right. Now, so now, what's happening is, and I think I'll say this orally, not right on the blackboard. We have this given a optimal strategy for player one in the infinite stage game. Player two looks at this optimal strategy. He knows what the strategy is, so he can update. His original probability for the left or the right game is a half, but now seeing what player one does, conditional on what the true game is, he can deduce something about the probability of the left or right game. So the event that we're talking about is, let's say, that the true game is nature chose the left game. All right? Now, as time goes on, you get more and more information. These probabilities, because of the probability convergence theorem, must converge. Okay? So after a while, they are within a small distance of some fixed number. That fixed number, let's say they converge to p infinity. All right? The P2's posterior probabilities that for L converge say to P infinity. Okay? Now, this P infinity can be different for each point in the probability space. In other words, player one can use mixed strategies. And depending on what he did in the previous play, he can use different mixed strategies, okay, on subsequent plays. So we have a whole big probability space. And the probability space, what does it tell us? How he actually played in previous plays. How did it actually come out? All right? So there are very many different possibilities. We have a big probability space. P infinity is a random variable, okay? It can be different depending on what happened before. But it always converges. There is some P infinity, no matter what the state of the world is, no matter how the mixed strategies of player one and player two worked out, you get a convergence to a fixed number. All right? Now, when you get convergence to a fixed number, that means that player one, in the later stages of this convergence, he cannot play very differently in the left game and the right game. Here they are. He can't play, once way down here, when we're close to P infinity, you can't play very differently in the left game and the right game, because if he played differently, then you would get a radical change in P infinity. And it's not changing, it's converging, right? So no matter how these things develop, you get after a while, player one is not going to be able to use his information. And it's not because somebody is forbidding him, but because of the probability convergence theorem. No matter what he does, he eventually has to stop using his information. And at that point, the game will look, what will it look like? So we have, with probability P infinity, we have, we have this game with probability P infinity, and this game with probability 1 minus P infinity, all right? And it doesn't change anymore. He doesn't reveal any more information. So the game is P infinity 0, 0, 1 minus P infinity. Okay? That's the game which you're facing once you are getting close to the limit of the probabilities, and the fact that you're at the limit, that you're close to that there is a limit to the probabilities is assured by the probability convergence theorem. And what is the value of this game? The value of this game is P infinity times 1 minus P infinity. That's the value of this game. Value of this equals this. Okay? Because optimal strategies for player one are to play 1 minus P infinity here, P infinity here, and for player two, the same thing. 1 minus P infinity here, P infinity here. Okay? Those are the optimal strategies, and you get this becomes the value. All right? So So depending, if player 1 in fact uses, if he doesn't use his information at all, then you get a quarter all the time. If at some point with some probability there's a possibility that he uses the information, then something will happen, and in the end we'll get convergence, and the result will be that the payoff will be p infinity times 1 minus p infinity. Now that's always less than a quarter. Yeah. The maximum of this expression, when p is between 0 and 1, the maximum of this expression is reached when p is equal to a half. And then the maximum is 1/4, okay? So if player 1 tries to make use of his information, and then we can assume that player 2 knows the strategy he's using, then we're going to get probabilities different from a half in the limit, some probabilities, and all of these will be less than a quarter. The result will always be less than a quarter. Okay? So what does he gain? He's lost, yeah? He's lost. So there's no sense in his doing this. He better not make use of his information at all. And so in other words, we have proved, where did we have this number 2? This. So this we proved in the beginning, and now we've proved this also. Okay. Are there any questions? This is, are there any questions? No questions? Crystal clear, like Frank Hahn used to say, yes? Okay. How is Frank, by the way? Do you know? What's that? Oh, he's no longer with us. Oh, that's right. I did hear about that, and yeah, I forgot that. Yes, with age you get loss of short-term memory, loss of long-term memory. Okay. Yeah, I did hear about that. All right. Let's now take a look at another game. And this other game is -1. -1. Okay. Not, sorry. -1, -1, -1. All right. You take a look. All right. Now over here, if player 1 wants to reveal his information, if player 1, in a one-shot game, obviously player 1 would play down over here because 0 is the maximum he can get. He would play down. Over here he would play up. Okay? And that way he can assure himself of 0 in the one-shot game. What about a two-shot game? Well, if he plays this, if he plays down over here and up over here, he'll be giving away the game. He'll be revealing his information. That's no good, right? No, wrong. In this case, it's okay to reveal your information because in any case you can't get more than 0. Player 1 cannot get more than 0. And he can assure himself of 0 by giving away his information in the first place. So the player 2 will know that, let's say he plays over here down, okay? And that's his strategy, to play down over here. Then player 2 will know that this is the right game. So what can he do about it? He can't do anything about it, yes? What can he do? He can try to get, you see, if player 1 gets -1, player 2 gets 1, he can try to play here. But that's no good. Player 1 will play down always, yes? So player 1 can assure himself, the best he can do is to reveal his information right away. And in that case, the value of gamma infinity is 0. It's not -1/4, it's 0. So what do we have over here? We have, in the first case, when we had a plus over there, we had a pooling strategy. What economists call a pooling strategy, okay? In other words, you do not take your information into account. In the second case, when you have a -1 over here, you have a separating strategy, all right? And that, the best you can do is a separating strategy. Now let's try another game. I can do this over here. In fact, let me keep this on. Board rubbery, lesson number 1. Okay? Follow Professor Gill's advice. Okay, the game that we're going to look at now is this one, a half. And this is not a 2x2 game, it's a 3x2 game. And it works this way. We have over here okay. Now again, we'll look at gamma infinity, and we'll see what's the value of gamma infinity. Well, let's try a pooling strategy first. The pooling strategy, we take half of this and half of that, so we get pooling strategy. This is pooling. We get 2, 2, 2, 2, 0, 0, right? Half of this and half of that gives you that, okay? The value of this game is 0, right? Because player 2, the uninformed player, can play in the middle, get 0, okay? So the value of this game is 0. Let's try separating. Well, separating, that means that you're going to give away the game. In other words, the player 1 will play up over here, down over here, right away from the start, and the result is that he gives the game away. So player 2 knows which game it is, and he'll play right if it's the first, if it's left, he'll play this right all the way on the right column if it's the left game, and the left column if it's the right game, okay? So again, separating, value equals 0. So neither pooling nor separating will gain player 1 anything. So is the value in fact equal to 0? No, the value is not 0. Question, answer, no. Value is greater than or equal to 1. Okay? How can player 2, so what I have to show you, in fact the value is 1, but at this point I'm just going to claim that the value is greater than or equal to 1. All right? Now, how can player 1 get 1? Get at least, what is it, what can he do in order to assure himself of 1? So here's what he should do. He takes a biased coin. The coin has probability of heads 3/4 and probability of tails of 1/4. He tosses the biased coin. If the coin comes out heads, then he plays up over here at the very first stage. He plays up, okay? And if this is the true game, he plays down. So if the coin comes out heads, he gives the game away. But if the coin comes out tails, he does it the other way around, okay? He makes believe that, so if the coin comes out tails, if this is the true game, he plays down. And if this is the true game, he plays up, all right? That's if the coin comes out tails. So in a sense, he's lying, all right? He is making believe that it is, that the true game, he is informed. So the player 2 sort of in some sense asks him which is the true game. So with probability 3/4, he tells the truth. And with probability 1/4, he lies, okay? And player 2 knows this, okay? That's the point. Player 2 knows this. So when player 2 hears that, when he sees that player 1 is playing, or when he hears, player 1 can even say, hey, this is the left game is the true game, then player 2 attributes to this only probability 3/4. He does not attribute it to probability 1 because he knows that the player 1 strategy is to lie with a probability of 1/4. So he attributes, if he sees player 1 playing up over here, he attributes probability 3/4 to this game and 1/4 to this game. If he sees him playing down, the other way around. What is the do we have any space left on the blackboard? No. All right, we have to start re-erasing. Yeah, we can erase here. Okay, so we get probability of 3/4, say, of this game, 3/4 of 4, 2, 0, 4 minus 2, 0, plus 1/4, if this is the true game. And then player 2 will figure that this is the true game with probability 3/4, and this is the true game with probability 1/4. Okay? What is that? 3/4 of 4 plus, sorry. Three-quarters of 4 is 3. 1/4 of 0 is 0. So we get 3, 3. Over here, we get 3/4 of 0 is 0. 1/4 of 4 is 1. So we get 1, 1 over here. And 3/4 of 2 is 1.5. 1/4 of minus 2 is minus a half. So we get 1.5 minus a half is 1. And over here, it's the other way around. So we get minus 1. Okay? That is the game. After player 1 has announced this strategy, player 2 can deduce that the true game is this one. not that the true game, no, no, sorry, not the true game, but the average of what he thinks. The probability, his expectation of what the true game is, his expectation is this. Okay? Now, player 1 will now play up because he said he's going to play up, right? It's with probability a quarter he's lying, but with probability 3/4 he's telling the truth by going up. So player 1 plays up. All right, what can player 2 do? He wants to minimize the payoff. So he'll take either this row, this column, or that column. All right? Payoff. One. Okay, not 0, it's 1. And similarly, if player 1 goes down, and he's signaling that it is this game, and also you get a payoff of 1. So here we have neither pooling nor separating. Neither one, all right? We don't get not pooling, not separating. We get a situation where it's partially separating, where he hints at one game, but the hint is not reliable. It's only with probability 3/4. It's not 100% reliable. He can rely that the hint is with probability 3/4 correct. But that yields him a payoff of 1, not a payoff of 0. Okay, so we have 3 cases, pooling, separating, and neither. What can we make of this? All right, so now we're going to state and prove a general theorem. And the theorem is this. We're going to denote by U the value of the infinite stage game when P1 ignores his information entirely. Okay? This is just to repeat it. When the informed player ignores his information entirely, then we get just it's a repeated 2-person zero-sum game, so it's the value of the one-stage game when the informed player ignores his information. So that we call that U. And the secret of making sense of these 3 different cases, pooling, separating, and neither, is to look at this value as a function of the probabilities. Up to now we've been looking only at the probability of a half. We let this half vary. Why do we do that? Well, the analysis that we've had up to now leads us to think that different probabilities are going to be relevant. You remember in the first case we had the P infinity. In this last case, we went suddenly from a half to 3/4, 1/4. Okay, so other probabilities appear to be relevant. Okay, so now let's question. Yes.
Is this equilibrium subgame perfect?
No. There's no subgames here. There are no subgames. This game has no subgames.
Okay.
All right.
Okay, like sequentially perfect. So
What's that?
Sequentially perfect. So once you are in the wrong, once you made the wrong, once the coin flipped 1/4, yes, I am actually choosing the bad outcome for me.
Yes. Yes. You have to keep choosing the bad outcome for you. Right. You have to keep choosing the bad outcome. You have to keep choosing it. Don't give the game away. I should say this. This is a proof of what the value of the infinite stage game is. But we're not saying anything about player 2's strategy, because this assumes that player 1, the informed player announced his strategy. He doesn't have to announce his strategy. Yes. Player 2 cannot depend on one announcing his strategy. Certainly he can't depend on him telling the truth, okay? So there's a question of what player 2's strategy is to attain this 1/4 in the first game, to attain the 0 in the second game, to attain the 1 in the third game. What must player 2 do to assure this? This is a totally different kettle of fish. I'm not going to go into that today. It's in the book, okay? It's in here. All right? And in here also. Okay? But we don't have time for that today. All right? So we're going to look at let U of P be the U of P is be the value of the one-stage game with P1 ignoring his information and probabilities P1 minus P. Okay? So we denote that by U of P. Now what we're going to prove is this. Now if we have let U cav, okay, denote the concavification of U. What is a concavification? Concavification is the smallest concave function that is greater than or equal to a given function. So if this is if U looks like this, okay, then the concavification of U looks like this. Okay, U cav. All right. Sorry. The smallest concave function greater than or equal to throughout a given function is called the concavification of that function. And excuse me? What's that? One stage game with P1 ignoring his information and probabilities P1 and 1 minus. What's that?
What is the probability P1
The probabilities of left are P and of right are 1 minus P. Okay? Of the left game. No, there's no coin. Nature chooses a coin. Remember the beginning here. Nature chooses this game with probability a half and this game with probability a half. All right? So this, instead of a half, we have P over here. All right? The beginning, remember the statement of the problem at an hour ago, okay? The problem is nature chooses one of two games, informs one player and doesn't inform the other player, and gives probability a half. I say, no, let's give probabilities P1 minus P. All right? You look worried.
I get what you but I don't know.
Huh?
I think I get it. But
Okay. All right, everybody else gets it, Elon. Okay. All right. So, in other words, at the beginning we had 1, 0, 0, 1, we had half, half. Instead of that, we put p and 1 minus p. So now our theorem is value of gamma infinity of p. Okay? So let's say we take, like I was saying, instead of 1/2, we take this, p, and 1 minus p. This is gamma infinity of p. All right? Is the concavification u cav of p. So if the original u was this and p is over here, then we will get this. Not this. So player 1 can gain from his information if he is in that part of the graph where the concavification is greater than the original function. And let's try to prove this, and then we'll give some examples. So, proof. The first thing we're going to prove is, the first thing, lemma 1, in a two-person zero-sum game, extensive game, no player can gain by having information withheld. Okay, this is there's in a non-zero-sum game. This is not true. Sometimes you're better off with less information. There's a 2 islands story. Who did that? I forgot his name. The 2 islands with rain on one side and on the other side. Huh? You don't remember? You're an economist. It's possible that a situation with less information is more beneficial than who came up with that example? Hirschleifer, that's it. Thank you very much. I knew you were an economist. Yes. Okay. Hirschleifer, that's right. But in a two-person zero-sum game, that can't happen. You can't gain from having less information. All right? That's lemma 1. I'm not going to prove it. It's very simple. I mean, you can just ignore your information. Okay? Okay. Lemma 2. Val gamma infinity of p is concave. All right. How do we prove that? Well, what we have to prove is that must prove that val, I'll just write val, val gamma infinity of theta p plus 1 minus theta q is greater than or equal to theta val gamma infinity of p plus 1 minus theta val gamma infinity of q. Okay, that's concavity, right? That is concavity, and I think this is this follows from this picture. First, nature chooses left or right with probability theta 1 minus theta, and then if it chooses left, then it chooses left or right with probability p 1 minus p. On the other side, it chooses q 1 minus q. Okay? And then in this case it's left, and in this case it's right. All right? That is now the top line is, but player one is, the informed player is informed of both choices. The top line here is if player two is informed of neither choice, then you get theta p plus 1 minus theta q. Okay? For, wait a minute. No, I got it wrong. Right. That's it. Okay? That's it. You have the probability of L as theta p plus 1 minus theta q. Okay? That is, if player 2 is informed of neither choice, that is the top line. If player 2 is informed of the top choice but not the bottom choice, then we get line 2, because then we essentially have two games, and this is gamma infinity of p, and this is gamma infinity of q, and you get one with probability theta and one with probability 1 minus theta. So the so we get so now here player 2 has less information on the, or has more information on the bottom part, right? Player 2 has more information, so player 2 is better off on the bottom part, so player 1 is less well off, okay? Zero-sum game. So that proves this, and now now we're going to prove lemma 3. Val gamma infinity of p is greater than or equal to u cav of p. Well, how does that follow? Well, it's certainly greater than or equal to u of p, because again, player 1 can simply ignore his information, and then he'll get u of p. So it's certainly greater than or equal to u of p. But it's also concave because of lemma 2, right? So since it's concave and greater than or equal to u of p, it's greater than or equal to u cav of p. Okay? So that's lemma 3. And lemma 4 is that, and that's the end. Lemma 4 is that the val is less than or equal to u cav of p. Okay? And how do we prove that? So again, this is very similar to the proof of that the value in the first case we looked at was 1/4. What happens? Eventually, because of the probability convergence theorem, so again, we say let us be given an optimal strategy of the informed player. We can assume that the uninformed player knows this optimal strategy, so he can deduce conditional probabilities from it. These conditional probabilities must converge. They converge to P infinity, say. And what we get then is this val of gamma infinity of P is the expectation of u of P infinity. Because again, when we arrive close to P infinity, then player 1 can no longer reveal any information, can no longer make use of any information, because making use of it would reveal more, and then we will not be converging to P infinity. So it is the expectation of u of P infinity. Now, this is less than or equal to the expectation of u cav of P infinity, right? Because u is less than or equal to u cav, right? We see this, right? U is less than or equal to u cav, all right? But this is a concave function. U cav is a concave function. So we can take it into the, we can take the expectation in. So this is less than or equal to u cav, the expectation of a concave function is less than or equal to the function of the expectation. So this is less than or equal to u cav of expectation of P infinity. But what is the expectation of P infinity? P infinity are the conditional probabilities. The expectation of P infinity is P, right? So this is u cav of P, all right? And that proves this. And together with that, this theorem, okay? And let me just finish up by giving the concavification of our three examples. Now, the three examples, the first example was remember, one was, well, it was P 1 minus P 0 0. So val is P times 1 minus P, which is this parabola. Okay? And the concavification is the same as it. Okay? That is example 1. The second example, the parabola goes this way. Minus P minus 1 minus P, 0, 0. Val equals minus P, 1 minus P. So this is the function u, okay, u, and what is the concavification? It's this, right? So the value is 0. That's the value of this game. Value of gamma infinity equals so val of gamma infinity is 0. Okay? In the third example, well, we didn't work out what the u function looks like, but we have some data points, okay? The data points were, remember, the separating was 0, 0, okay? The pooling was also 0, but then 3/4, 1/4, 1/4, 3/4, these were 1. Okay, so those are the 5 data points that we have. Now, homework, go home and figure out that this is the U function. The U function looks like this, and the concavification is this. Okay? And so we have our 3 examples bear out the final theorem. This is as far as I'll go today. We have said nothing about player 2 strategy. We have said nothing about non-zero sum games. This is just the beginning. It's in the very first chapter of the book by Marshall and me, and it's also, of course, in the Saran Martin Zamir book, and it's just the beginning of this fascinating area of study. And if there are any questions, I'll be glad to answer them at lunch, because it's 1 minute after 12. Okay, thank you very much. Oh, wait. Do I have time to talk about this? The significance of, yeah, I guess, what? Yeah. Optimal strategies in the infinite stage game. Wait a minute. We have to turn, let's wait until this. Our IT man gave me the wait sign. Doesn't work? Doesn't work. Okay, look here. Okay, the significance of V infinity, in other words, the value of the infinite stage game, the limit of the end stage game, and the limit of the discounted game. So optimal strategies in the infinite stage game are approximately optimal in each sufficiently long finite stage game. So we're talking about one strategy, and that's going to be approximately optimal in each finite stage game, okay? So if a player knows that the game is long, but he doesn't know how long, he should use optimal strategies in V infinity. Optimal strategies in the end stage game depend crucially on n, okay? And similarly, optimal strategies in the discounted game depend crucially on the discount factor. The advantage of the infinite stage game is not because I believe that really there are going to be infinitely many stages, but because optimal strategies there don't change with the parameter. They don't change with n. They don't change with delta. Maybe you won't get the exact optimal in the end stage game, but you'll get close to there, okay? And the delta discounted game is like the end stage game in that its effective duration is finite. It's unlike the end stage game in that it admits stationary strategies and it rules out pathological end effects. Okay, so that is the end of the talk.